Okay, in this question, they want us to discuss whether the function is increasing or decreasing. Now, these are all exponential functions, and exponential functions always have an exponent with a variable. Now, when we're looking at these, b is the base. Be careful, it's got to be the base. And if it's greater than 1, we say it's increasing. And when I say that, I mean the function values, those y values from left to right are going up. If it's between 0 and 1, we say it's decreasing. And that would be because of the values are going down. And it's not a straight line, it's a curve. But the values are going down from left to right. So this should be an easy problem. We just look at the base. Now, the base of A is 0.5. And 0.5 is between 0 and 1. So we're going to say it's decreasing. Okay? Let's do the next one. The next one also has a B. When you look quickly, you say, oh, the base is 3/8. But be very careful. This is a gotcha type problem. If you notice, the exponent here is negative. And when the exponent is negative, if you remember, to make it positive, we could switch the locations of the numerator and the denominators. So we could write this as 2/5 times 8/3 raised to the x. So don't make a judgment call until you've made it a positive exponent. Now we can see that b is 8/3, which is greater than 1. So therefore, our function is increasing. How about this third one? Well, this one here, our exponent is x, and that's positive, and our b is 0.75. And we can see that's between 0 and 1. So our function is decreasing. Now it also asks you to find the y-intercept for these three problems. And this is, no matter what we do in this entire chapter, this entire semester, y-intercept is always defined as where x is equal to 0. It's on that y-axis. Every value on the y-axis has a 0 in the coordinate pair. So let's just put in an x equal to 0. So y is equal to 5/4 times 0.5 raised to the 0 power. What's so great about this is whenever you raise something to the 0 power, it's equal to 1. So the y-intercept is 5/4. So you could write that as an ordered pair if you like. Let's try the next one. Well, we know that the exponent, the base raised to the 0 power is going to be 1. So it's going to be also 2/5. And then last but not least, c. Well, if we put in a 0 for exponent, 0.75 raised to the 0 power is also 1. So our y-intercept will be 1.3. We can write it as an ordered pair. Our next problem, part A, asks us to state any vertical and horizontal transformations. Let's just talk about all the transformations for this. These work exactly the same way we did earlier in the semester. We said that when we have a constant just outside of the function, outside by itself over there, then this is going to tell us up or down, right? So this -4 is telling us to go down 4. If it had been a +4, then I would go up 4. Okay? Next, we want to look for a horizontal or vertical shift, and we can see that if there's a plus or a minus number with the x, then that's going to be a horizontal shift. So this is going to be, it says +3, but just like we did earlier when we talked about basic functions transformations, if it says +3 for the horizontal shift, we're actually going to go left 3. If it said -3 there, we would have gone right 3. I know this one always seems backwards to me, but if you graph out the points, you're going to see this is true. Okay, it's just like the basic function transformations. So these are the vertical and horizontal transformations, but as long as they have it in here, they also have a minus in front of base. And since the minus is in front of the base, it's telling us that we're going to reflect it. It's going to mirror about the x-axis. just like we did with our basic functions. We said that if it is in front of this, you're going to have mirror about the x-axis. When is it going to mirror about the y-axis? Well, yeah, that's when it's, that would have been had we had a number in here, had we had a negative in front of that little x. Yeah. So those are our transformations. B asks us to find the horizontal asymptote. So let's just think about this. We know that the basic function for an exponential looks something like this, right? It has an asymptote, horizontal asymptote of 0. But you just told me in the last part, we are going to shift down 4. So my horizontal asymptote has shifted down 4. So now instead of being y equals 0, it's going to be y is equal to negative 4. Okay? Part C says, find the y-intercept. And like we said in the last problem, y-intercept always means the same thing. At the y-intercept, x equals 0. So I'm just going to put in a 0 for x. And I'm going to get negative 2 raised to the third power minus 4. Now, be very careful here. You remember we talked about bases. We said that the exponent would have to reach out and touch whatever the base is. So only the 2 is the base. The negative is not. So this is negative 8. So our y-intercept would be 0, negative 12. And part D wants us just to make a quick sketch of this. So we know that we're going to have an asymptote at y is equal to negative 4. I'll just draw a little dotted line here. Okay. And we know that our function has been shifted down 4 and shifted left 3. Okay, so we're going to move to the left 3, and we're going to mirror it about the x-axis. And then last, we're going to have a y-intercept right here. Sometimes it helps to sketch in the real function, the basic function. We're just going to call this one, let's just call this one 2 to the x, right? That's just kind of a sketch of that. So if we were to do the different steps, if we shifted it down 4, it would look something like this. And then if we shifted it left 3, it would just move over. So it would go a little more like this. And then if we mirror it about the x-axis, it's going to go the other direction. And that's all they're looking for, just a basic shape of what it's going to look like. So this will be our new function, negative 2x plus 3 minus 4. Let's do it again. We can do this. Okay, so any transformations, we can see that we have a plus 5. Just like before, this means we're going to go up 5. And next we look for the horizontal shift. We look where the x is, and it has a minus 1. This is the tricky one to me. This is always, my brain has to think about it. I'm not going to go left 1. I'm going to go right 1. Okay. And this is always true unless I told you in the very rare place that you have that, that mirroring about the y-axis, and then it doesn't, then you do go right for a plus and left for a 1. So I'm just saying, just in case you ever did see that, if you have a minus in front of here, then it would change. You would go right 2. Okay, and that's all we have. And then state the horizontal asymptote. Well, we know for any exponential, the horizontal asymptote of the basic function is going to be y is equal to 0. But since when we went up 5, we're going to say y is equal to 5. Find the y-intercept. The y-intercept is when x is equal to 0. So if we say 3 and we put a 0 in for x, 3 to the negative 1, that's going to be 1 over 3. So our vertical intercept would be 0, 5, and a third. Or you can give it as an improper fraction, that's fine either way. Transform this sketch together. So this was our basic function. I'm just calling this kind of a sketch of 3 to the x. And if it goes up 5, we know we're just going to lift the whole thing and raise it by 5. And then if we wanted to go right 1, it just means it's going to shift a little bit to the right. And this is our transform function here. So just a quick sketch to follow the directions of the transformation. For each function, state whether the graph of the given equation was reflected about the x, y, or neither axis in comparison to this basic function for the x. We just talked about this a little bit. So you look at the function. If the minus is in front, like this one here, then we know we are reflecting about the x-axis. If you have a minus in front of the x in the exponent, then we know we're reflecting about the y-axis. That's an easy one. Okay, find the exponential function for each graph. So we're given 2 points. We're given, first of all, this nice anchor point right here. This one's important, 0, 1. I know that my exponential, it comes in the form of y is equal to a times b to the x. So if I'm given 0, 1, I always start there. This is a nice, easy one. That tells me that when x is 0, y is 1. So let's just put this into our equation. So we say 1 is equal to a times b to the 0. What's so great about this one is because whenever it's 0, 1 for the y-intercept, we know that a is equal to 1. So we don't have to worry about a. So now we're going to take the second point. We're going to use our equation again. This time we know that a is equal to 1, so we don't have to even write it in there. We can leave it as just y is equal to b to the x. Now let's replace x with 2 and replace y with 17.64 because these are the 2 points that we're given. We're given this point and we're given this point. And each point has an x and a y. Okay, so now all we need to do is take the square root of both sides. And we know this will be plus or minus the square root of 17.64. Now, by definition, we say an exponential, b must be positive base. So we're only going to use the positive b. Now, don't get confused. You might think to yourself, wait, sometimes there's a minus in front of that b. Well, remember, if there is a minus in front of the b is the base. It's whatever that exponent could touch. The negative is just a number in the front. It's like having a -1 in the front. So this is still exponential. What it's saying is you cannot have this. You can't have negative b to the x. That is not exponential. So we're only going to look at the positive root, and we're going to say y is equal to 4.2 raised to the x. And this is going to be our answer. Let's do another one just like this. So once again, we know an exponential function has this as its form. Since we have 0 and 1, we know a is going to be 1. So actually, let's fix this. We know that an exponential actually has a coefficient here you could put a. But since we have 0, 1, we know that if we put in a 0 and a 1 in for x and y, a will equal 1. So we don't even need to deal with a. So instead, we're going to say y is equal to b to the x, and we're going to replace x and y with -2 and 7.11. Okay, so we know that this means it's in the denominator. Another way we can think of this is we can just raise this to the -1/2. You could do it either way. You could move the denominator, and then it would either way would work. But we're basically taking the square root of both sides in the denominator. So this is a pretty straightforward one. 0.375 raised to the x equals y. Now, the next problem deals with growth and decay factors. So let's review. For an exponential growth or decay model, we use this format. We say that we use instead of an A, we use P initial. So P initial means what is it at the very beginning when time starts, okay? Now our base, if it's greater than 1, we know it's increasing, so it's growing. If it's between 0 and 1, we know it's decreasing, so it's decaying, okay? R is the percent increase, or the percent decrease. Now you find that R, it's part of the base. So if my base is like 1.2, then my increase is 0.2, which is 20%. If my base is 0.5, then it means 1.1 minus 0.5. So my R is 0.5 or 50% decrease. So that's where you find the R. Okay. So let's look at our problem. The first one says, what is the initial value? Initial value is always that A, that coefficient in front of the exponential function. So our initial function, P0, is 3/4. For B, it says, what is the growth rate or decay factor? Now, we can look at this B, and the B tells us, is it increasing or decreasing? We said that if it's greater than 1, it's increasing. So we're clearly increasing, so we're growing. So we're going to need a growth factor. So our B is 1.82, so that's going to be a growth factor 1.82. The last part says, what is the percent increase or decrease? Well, we're increasing, and all we need to do is we look at our growth factor and we say 1.82, that's bigger than 1. So we're going to subtract 1 out of there, and we'll say it's 0.82 growth, which is 82% growth. All right, let's look at the next part. Why don't you stop and try it before I give you the answer? Okay, so the initial value is going to be 0.8. Is it going to be a growth rate or a decay factor? Well, we look at the B, and since B is between 0 and 1, it's going to be a decay factor. And then we say, well, it's 1 minus 0.95, give me 0.05, so that's 5% decay. So when you're looking for the growth or decay, look at these and say, like for example, the one above it, that's 0.82 bigger than 1. How much is this less than 1? That's you're comparing it to 100% or 1. Okay? And is it an increase or a decrease? Well, it's going to be a decrease, it's decaying, of 5%. Let's try a word problem. Remember, step 1 is always understand the problem. So pause the video and read it to yourself. So this equation models how many wild Florida panthers there are. Okay, and T is the number of years since 1900. That's really important to realize how T is defined. What is the value of P at 0? In other words, the initial P. We know that's that A value. So it's going to be 25.31. And if we wanted to say this in a complete sentence, we would say that in 1900, there were 525.31 panthers. But we realize that panthers don't come in parts. So we could instead, if I want to use a sentence, I could just say, in 1900, there were around 525 wild panthers. That makes more sense. Now, identify the growth or decay factor. We know in a function, the B is going to be the growth or decay factor, and it's 0.997. And since it's between 0 and 1, it's going to be a decay factor. Identify the percent increase or decrease. Well, it's decreasing since it's decaying, and we just ask ourselves, off of 1, how much is it? Well, 1 minus 0.97 is 0.03. So that's going to be a 3% decrease. And then it says find P at 64. So P at 64, that means that this is the time after 1990. So in 1964, how many panthers were there? So I would need to calculate this. So I'm going to say 525.31 times 0.97. And in place of T, I'm going to write 64. I'm going to use my calculator, and I get around 74.78. But we realize panthers don't come in parts again. So in 1964, there were 75, we'll put around 75 wild panthers. Okay, and that'll be part D. And then last part E says, use the model to approximate the number of panthers in 1990. So 1990 is 10 years, no, it'd be 90 years, sorry, 90 years after 1900. So T is equal to 90. So let's go ahead and put that into our function. We get 33.87. So we'll say in 1990, we can expect only around 34 wild panthers. Wow, they're losing a lot of wild panthers, aren't they? Okay, let's try another one. Go ahead and pause the video and read it. Make sure you understand the problem. Now we're imagining that we're scientists. Okay, there's an initial population of 250 organisms, and we're growing, we're increasing by a factor of 2.3. So A says, write a function where T is the time in weeks. So our initial population, we know we're going to always put initial, and then we're going to do B to the X. So our initial will be 250. And then our growth rate is 2.3. So our function is 250 times 2.3 raised to the X. B, find the number of organisms after 9 weeks. So this is not hard. T is a time in weeks, so we're going to put that as in for T. So after 9 weeks, we're going to have a lot of little organisms running around. And then let's try it for after 1 month. So we have to say to ourselves, how many weeks is 1 month? Well, there are 4 weeks in a month, so we're going to put 4 in 4T this time. And I got 6,996. Okay, now the next problem is a word problem. So we're going to pause again and understand the problem. So we're talking about a doctor and he's investing money. So when you're investing money, you call that the principal. So he's investing $80,000. Sometimes you'll borrow money and we also call that the principal. And it says it's paying at 4.25% interest. That's going to be our rate, our interest rate. And we always enter it in as a decimal. So instead of a percent. So 4.25% is going to be 0.0425 as a decimal. And then T, we don't know. That's the time in years. Okay, but we can go ahead and find out. It says, write a function for the amount A in the doctor's account compounded annually. So when it's compounded annually, it'll simply be A function of time. So it'll be 80,000 times 1 plus 0.0425 raised to the T. Or we could write that simply as 1.0425 raised to the T. B, how much money will the doctor have in the account after 8 years? So in other words, when T is 8, what will our account balance be? So we're just going to put in a T of 8 and evaluate it. I calculate that I'll have around $111,609. Part C says to graph the function and locate your answer from part B. You can see all they're caring about is that you're seeing that it's increasing and you understand that when T is 8, it's going to be 111,609. Okay. Part D, from your graph, estimate when the doctor will have approximately $100,000 in the account. Okay, so this is not the best graph to estimate off of. I should have done a little more carefully if I wanted to actually use this graph to estimate. So let's use our calculator and have a little better graph. So I went ahead and changed my windows just so that I'll have be able to see everything since I'm dealing with such big numbers. And then if I graph it now, it looks like this. Now it doesn't look like it's curving, but we know it is curving. I could use my table, second graph, and if it wants to know approximately where there's 100,000, I can come over here and say in about 6 years, you can see it's about 100,000. Part E asks me to find and interpret the vertical intercept. Well, this is not a problem. We know this is just when t is equal to 0. So when t is equal to 0, it's 80,000. So I could say that my initial value in my account was $80,000. That would be part E. And part F says determine the domain and range in terms of the problem. So this is not just given this equation. It's saying using some reasonable restrictions. For example, time can only go from 0 forward. You can never have negative time. So our domain is going to go from 0 to infinity, right? So our domain would be from 0 to infinity because of time can't go negative. And therefore our range similarly will be from $80,000 to infinity. Because at 0, it's 80,000. And I guess if you left it in there long enough, it'd be infinity. Now, sometimes in these problems, when they ask you for the domain, the range, and they ask you to be reasonable, they ask you basically to consider what your graph shows. So instead of infinity, we could say reasonably, that's going to be looking more in the 10-year area. So I said my graph was around from 0 to 10. So I could limit my domain to 10, and then I could similarly limit my output to when t is. So if you're doing a multiple choice problem and you notice this is what they're giving you, that's because they're just considering what is reasonable on the graph that you can read. So they're saying a window of 0 to 10 years.